Voilà, ben on va reprendre. Donc le séminaire d'aujourd'hui est donné par Guillaume Bossard de l'École polytechnique, qui a sorti il n'y a pas très longtemps un article sur E11, maybe I switch to English, E11 Invariance of Supergravity. So the idea is to try to make explicit the mysterious hidden symmetries of which we see signs here and there, and they have a work where they establish to a large extent the E11 invariance of supergravity. And I think this is a very important piece of work which is expressed in terms of mathematics that we have not yet seen, but I think that Guillaume will be kind enough to review some basic aspects of Cas-Moody algebra. I'm saying that now because you told it to me, right? Sure. I don't want to put you in an uncomfortable situation. So as you will see, these huge symmetries are extremely fascinating. They are difficult to put in the limelight, and Guillaume will tell us more about that now. So please.
So thank you very much, Marc. And let me thank you also to give me the opportunity to give a talk in this nice lecture series. So I don't expect many of you to be familiar with hidden symmetries in gravity or supergravity. So I'm sorry for the expert, but I will start by reviewing some of these properties before to explain what we did. The main point, as Marc has kindly reviewed, is actually to understand better the hidden symmetry from a higher dimensional point of view and from the idea of something that I will call generalized diffeomorphism. But before to discuss this, I want to review a little bit what hidden symmetry are. And for this, for a first part of this discussion, I will come back to the 57th with the work of Ehlers that Bernard briefly discussed in his own lecture. So I start with just Einstein gravity. In 4 dimensions. With one isometry that Ehlers considered to be time-like. So the time is an isometry. And so the metric in that case simply reduced to ds2 minus exponential 2u of x dt plus omega I of x. I use as mark I for the space-like indices minus 2u of x, and I write the space-like metric gamma ij. So in that case, there is no dynamics because dxi, dxj, and this is a square. Yes, thank you, of course. This is bilinear. So the non-dynamical equation, just read in that case R0I of the metric is equal to 0, the Einstein tensor. And if one writes this explicitly, assuming that there is no dependence in time, one just gets a conservation equation, which read in that way, gamma I k, gamma I L, the inverse metric, of course, of the gradients di omega j minus dj omega. So by locally, at least by Poincaré lemma, and I forgot the factor for you here, by Poincaré lemma, one can define functions locally associated to this conservation. So I just write 1 over square root of gamma ij, s jkl, the epsilon antisymmetric tensor, Levi-Civita tensor, is equal to the gradient of some function psi. And so the idea of Ehlers is just to write all the equation in terms now of a scalar function, so-called Ehlers potential, which is psi plus I exponential to u. And all the equation can be written as a Laplace equation for this scalar function, complex scalar function, and that the Riemann tensor for the metric gamma is equal to minus 2 di e dj e bar. It's a complex function. Its imaginary part to the square. So what Ehlers realized is that this exhibits then an SL2 symmetry. The SL2 symmetry that you may have seen, which is if you write a matrix G, A, B, C, D, where the determinant AD minus CB is equal to 1, you have a non-linearization on the complex upper half plane, where you go from E to AE plus B divided by CE plus D. And this nonlinear symmetry is called a hidden SL2 symmetry, the so-called SL2 Euler symmetry. Now, once you have this, a way to understand this just from coset construction is that you can write an SL2 matrix, which is in a coset similarly to what Marc described in his lecture, that you can write as exponential minus u 1 psi exponential 2u 0, and consider the coset associated to this. So this parameterizes SL2 divided by SO2. And now I can write for M equal V transpose V, a current conservation, G, Ji, M inverse DIM. And because this current is conserved, I can define dual vector associated to it, which I write gamma ij epsilon jkl dkal. So those vector al, there are 3 of them now, and they generalize the vector appearing in the metric, the omega I. So if I write it as a matrix, I have AI equals some A2 AI0 plus AI1, AI1 minus AI0 and minus AI2. It's just the matrix for the SL2 Lie algebra, and this component is simply the omega I we started with. So a question that have interested physicists for some time, theoretical physicists, is that can we make sense of this symmetry, but directly in 4 dimensions? That is, get rid of this condition that nothing depends on time. Is it possible to have a realization of this symmetry? And there is the intuition that this symmetry gives rise to a generalization of Dirac U1 symmetry. So if you have Maxwell equation, you can write F and the Hodge dual star F and transform one into the other while preserving the vacuum Maxwell equation. And the idea is that this Euler symmetry is related to something similar, but now for the Riemann tensor. And so this is related to the idea of the dual graviton. Most of the attempts, however, fail. But there is a partial answer which may not be fully satisfactory. And which I think is mostly due to Home and Zemtleben, but which extend older idea to make sense of this. The idea is that to have this realization, you need to have, in fact, more coordinates. So instead of having only xi and t, you now include a ym, where m is an index of SL2. So there are 3 of them, just like the 3 components of these vectors that I wrote here. This ym comes with a natural Killing-Cartan metric, KMN, which is of Minkowski signature, and the structure coefficients of the SL2 algebra, which I write Sm and P. But in order to make sense of a theory depending on those 6 coordinates now, one has to impose a strong condition, which is called the section constraint. Such that for any field of the theory, there is a multilinear condition which states that if f and g are fields of the theory, depending a priori of x and y, then kappa mn d by dy m of f d by dy n of g has to be equal to 0. And the same for epsilon mn p. This is a very strong constraint, but as written in this form, it does not violate the SL2 symmetry because I just use SL2 structure constant coefficient, the Killing-Cartan form and the structure coefficient. And now if you solve this explicitly, well, the solution is very restrictive, in fact. And if I write y as y2, y0 plus y1, y1 minus y0, and minus y2, you can find that the field can only depend on one of them. This is easy from this because the structure coefficient just says that the wedge product is always 0. In fact, it has to be null, such that, in fact, there is always, for any y, a G orbit, SL2 orbit, such that you can write it as simply a matrix which only depends on time, where time here is thought to be this y0 plus y1. So if you solve it explicitly, you get back to four-dimensional gravity, but the formulation itself has a manifest SL2 symmetry. SL2 invariant, should I say, because it's not truly a symmetry, in the sense that if you act on a solution which only depends on this time, you will get another solution which will depend on another null coordinate in this three-dimensional space. But nonetheless, you can do that. To do that, I will not show it explicitly here, but there are some more things that are involved. For instance, you need to include this vector field here. And so the naive current, which I was writing as M inverse DIM, must now be promoted to a more complicated current, which starts with the same current, JM, but involve also the vector field that I had written through the structure constant. So M, sorry, I have to write this P. P QR of dq AR, the internal derivative here, and also an additional field which I write chi I P. This additional field that we will see later is some field introduced by Home and Zemtleben, which is called to be constrained as well. Meaning that for any choice of coordinates, you have also to constrain it. So essentially, for any function, you will have kappa mn d by dy m of f chi I n is equal to 0, and the same for epsilon. So this is a big price to pay, and one may wonder if it's useful to describe just four-dimensional gravity. So the motivation for doing this is not really from four-dimensional gravity, and now I will go to 11-dimensional supergravity to give more motivation to do this. Yes?
So you say that once you have introduced these extra variables and these extra fields, you have a formulation of four-dimensional gravity, which is manifestly SL2R invariant, or?
Yes.
Okay.
So you have a Lagrangian, which depends on the field I described, chi I, P, I, R, and M, with dependence a priori on 6 coordinates,
okay.
X, I, and M, and is invariant under a generalization of diffeomorphisms that act on this 6-dimensional space.
Okay.
But in order to show invariance, you need to have this to be satisfied for all fields of the theory. That is, all the identity you check are always true up to this algebraic identity.
And SL2R is part of the generalized diffeomorphism, or?
Exactly, yes. There is a generalization of diffeomorphism which acts exactly as SL2R. So SL2R is naturally associated to diffeomorphism, but in the fundamental representation, whereas here it's in the adjoint. And so the idea of exceptional field theory is to generalize that for any group, and specific representation. Also, in principle, one can do it for any representation. So let me go to 11 dimensions. So before to discuss the rest, I want to also say something about the work of Bernard Julia, who is right here. Coming back to Kramer, Julia, Scherk, 11-dimensional supergravity Lagrangian, which read as R of minus G R. So it's very similar to the writing that Marc used in his lecture. So it's the factorial 4 factor, exactly. We have the same convention. mu sigma rho, F mu sigma rho, for a 4 form. And one term that he did not include, which is important in 11 dimension, is the so-called Chern-Simons term. So here I just number them from 1 to 11. mu1, mu2, mu3, F mu4 all the way mu7, F mu8 all the way to mu11. So those are the field strengths for the abelian field, just like in the lecture of Marc. And in the form notation, one can write this as dA3 and write the Maxwell equation as dF4 is equal to 1/2 of F4 wedge F4, which shows by the Poincaré lemma that there is a 7 form, which write as d of a 6 form potential plus 1/2 of A3 wedge F4. So this is the duality that is already realized manifestly in 11 dimension. But what they obtain is that if you now consider this theory with 7 isometries, so essentially you say that your 11-dimensional space-time decomposes as a 4-dimensional space-time times a 7-dimensional torus, and you take the zero mode over the torus, the constant field over the torus, then you have a hidden symmetry, a very large hidden symmetry, such that all the scalar field of the theory now parameterize the exceptional symmetric space E7, 7 by SU8 by Z2. So this, in general, I will write K of E7, and I will forget about the 7 here index, which means that this is a real split form. So how does it go? Well, the V minus transpose involves all the field of the theory. So just to write it a little bit, there is the internal field bind, the one of the 7 torus which appear here, the power depend of the theory, but what I will write now does not really depend on it. So you have the internal field bind that appear here as a term. So it's a Iwasawa type gauge for the E7 coset that you get with block diagonal form, which take E1, E2 all the way to E5 here, A1 to A5. And here the last component, E time EAI. And all the off-diagonal component involves the potential of the theory. So maybe to gain some time, I will not write explicitly what it is, but essentially you have AIJK appearing in all off-diagonal, and for upper diagonal, you have the 6th form. And with this, you can show that you get this E7 formulation of the theory, where moreover, you have now 56 electromagnetic field, FMN, that satisfy to a duality equation. Let me write it with G. G mu sigma, G nu rho, epsilon sigma rho kappa lambda. So it's just Hodge duality, but now involving MP omega Pn, Fn kappa lambda. So this M is simply the product of the matrix V. M is equal to V transpose V. And omega is a symplectic form which exists on the fundamental representation of E7. So E7 includes this 56 representation, which decompose, which admit a symplectic that is a non-degenerate bilinear form. So once again, the idea of having a generalized diffeomorphism is to try to understand this symmetry, but from the point of view of the theory directly in 11 dimensions. And for this, one has to extend, once again, the coordinates. So in that case, the idea is to extend the coordinates yi over the torus to 56 of them. So there will be yi, yij, yi1 to y5, sorry, and yi1 to y7 semicolon j. So antisymmetric of 7 indices gives a scalar in 7 dimension, but I write it because it will show up in general. And the idea of this generalized geometry is to extend the notion of the vector space. So when you study geometry, it's very important to understand the tangent space. And now the tangent space is extended by the dual exterior product. So I define the exterior product of the tangent space to the power n as omega n for simplicity. And you see that this extended bundle, if you may say, extends that way. And I write omega 7 semicolon 1 for the tensor product of omega 7, omega 1. And so this will be the coordinate. So if you think of the diffeomorphism, the ordinary diffeomorphism on the torus, you can write their action as the usual transport term plus a rotation term, which is completely generic in that case. So you think of di psi k acting on jkj plus jik acting now with dj psi k as a matrix multiplication. And so the idea of generalized geometry is to combine all this now, but for the big matrix M, Mn, and to have a notion of generalized diffeomorphism, where you will write now for a parameter which include all the possible parameters here. Mn is equal to psi p dp mmn. But now, those matrices are just general GL7 matrices. What you want in the case of generalized diffeomorphism is to project them to the group that you're interested in. In this case, it will be E7. So you just project them by the fundamental representation. And you act now on those matrices exactly the same way, with M R M Rn plus M R T alpha Rn. So the question now is to make sense of this. Can you make sense of this notion of diffeomorphism? And one simple exercise one can do to see if it makes sense is that one would like to be able to derive a function. So if I derive a function, I want the function to transform as a diffeomorphism. A derivative of a function, sorry, as a diffeomorphism. So if I act on this derivative of the function, I will get by construction the usual transport term. And just by acting with the derivative, I get now psi n partial n acting on the derivative of my function, which I would like to call the transport term, and plus a rotation term, which takes this form. But for a general function, of course, this would be in GLN. So to impose some constraint, we want to impose by hand that this will be, in fact, equal to the structure I wrote on the left, meaning that this is T alpha PQ, dp psi q, acting with some T alpha n, mn, sorry, dn phi. In fact, to make sense of this, it's important to add a weight, but we allow for a weight, which will be covariant as well. So I add to this W dn psi n dm phi. And you may wonder if there are solutions to this problem. In fact, now, if you write it this way, it's just an algebraic question. Can you find solution to such a constraint? And there is a solution, but what you get now is that for any function, you will get the notion of section constraint, and you find for E7 that W is equal to 1/2. To minus 1/2. And in general, in fact, for ED algebra, you find this relation that this is equal to 1 over d minus 9. You may wonder what happened for 9, but it's not a problem. In fact, there is another formula. And so this is typically what I want to use now, but for a more general algebra. Is there any question now before I proceed? If not, so let me write now a Dynkin diagram, which was the one for E7 that we used so far. So each time I consider one more direction in the torus, one can show this is something that Bernard Juillard realized very early. It amounts to add a node to the diagram. The next step is to get E8, and E8 is a generalized naturally the Euler symmetry that I talked about in the beginning. If you go one more down, you get E9. Now it's not in the Cartan classification. It's a so-called affine algebra. And it's related to the integrability of codimension 2 solution in gravitational theories. And if you go one step down, this is the algebra that Marc will define for you in the following lectures, which is a conjectural symmetry near cosmological singularity. Which has nothing to do then with the torus a priori. And if you go one step again, you get to 11, which is the one I want to talk about today. So for the labeling, my diagram is not very pretty, but I will label the node 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and the 11th node is the one that makes the group exceptional.
The last one is 10.
Sure, thank you. The number were correct, but I don't want to call it 11 yet, otherwise there is a problem. So I will not give the standard definition of Kac-Moody algebra, but I want to give one which is related to the way we think of it in 11 dimensions. So if I define ED, the way to understand it from this diagram is to remove the 11-dimensional node and to think of, just like for an SL2 basis, you have an H generator, which in that case just corresponds to GLD. You have a raising generator, which is a tree form with respect to GLD, and a lowering generator, Fijk. Now, if I take this triplet, assume that the commutator of H with E is just what you should expect from the representation of GLD on Ijk. The same for H with the contragradient representation. And you take as a commutator Eijk with F LPQ the following. So delta with more indices is meant to be the antisymmetric part of it. And HKL minus 2 the trace of it, which is related to the D-1 factor of Marc in his lecture. And he miss K and Q here. So if you take this as an algebra, you can generate whatever comes out by multiple commutator of the E or the F on the left, and just eliminate whatever is a so-called ideal. That is something you can remove and get a simple Lie algebra, and you obtain the ED series. So that's a defining principle. How does it work? Well, if I take the commutator of Ijk, EPQR, there are more than one representation in general, but if you remove the ideal, you can show that there is only the completely antisymmetric LPQ. So for D strictly less than 6, it stopped before, and indeed it would correspond to the various groups that corresponding to this diagram. If you go one more step, you get something now with 8 antisymmetric indices. There is a factor here, JK LPQRS, antisymmetrized with another one. So it's what I would call a omega 8-1 tensor, meaning it's in the tensor product of an antisymmetric rank 8 with a rank 1, but without the completely antisymmetric piece. And it goes on and on. If you take E8, this is all what you have. And for affine, already you get infinitely more. The structure for affine is relatively simple, meaning that the representation you get just come out. Yes?
You are raising the case for D equals 9. So W is infinite. So
W is not infinite. So for you, I can say that in general, if you have a weight of a representation, the value you have is in fact lambda minus 1. And for affine, you have to add to the rank. So this corresponds to the effective rank when you have completed the Carter matrix. So it would be D equal 10 for 9. So the formula is regular. So if you take the representation that appear for affine is D equal 9, so you can get 9 form. The way I write things, you see that you can only get 8 form for E8 or greater D. And if I go to E9, well, I have the 3 form I wrote, the 6 form, the omega 8-1, and then there are just repetition of the former, meaning 9-3, omega 9-6, etc., until you get as many copies of 9 as you wish, and one of the previous 3, 6, or 8-1. And so this is the structure of an affine algebra where you just have repetition. In fact, you can relate this algebra to the algebra of function over EI. So you have a function of one spectral parameter valued in the Lie algebra E8, plus U generator I won't talk about. Things get much more complicated when you go one step further. So one step further, you have E10. And now at this level, you start also to get a 10-1-1 representation. And if you go further, there is no nice structure. In fact, not only there is no nice structure, but the number of irreducible representation you get is now non-polynomial. It grows exponentially. If you go to E11, you can now have E11 form, and you get one exactly at the same level. And once again, it grows exponentially. So in some way, E10 is better than E11 in a way that Marc will explain, that I won't explain. But in some other, you have the same very bad problem. But still, the Lie algebra exists. You can define representation theory. And so you can use it to define a theory. So one thing you can do in particular, and which I will use, is just take tensor product of highest weight representation. Just like for SU2, you all know that if you sum spin, you get all the spin between the difference of the spin and the sum of the other spin. Here, in the same way, you can take the tensor product of highest weight representation. As usual, you always get the double weight in the tensor product. But now the problem is that you get infinitely many irreducible representations. So this direct sum never ends. In the same way, I have an antisymmetric, which I will use later. However, for our purpose, what is important is that even if you have infinitely many irreducible representations that appear in this tensor product, you can still consider that what is after the first representation is much smaller than what is here. So what I will use instead is writing, instead of a direct sum, some reducible representation, which I write L of lambda 10, because the first weight is lambda 10, and L of lambda 4, because the first weight is lambda 4. And this is the only thing I need to remember. So what will correspond to the section constraint now is that when you have d by dy of f d by dy on G, it vanishes if it's in one of those representations. So now I can go a little bit more about, talk a little bit more about the theory. So to do that, I need to define the scalar in the same way. But for E11, there is no external or internal space. There will be E11, sorry. There will be only the internal space, and the internal space is associated to the highest weight model associated to the first node. So it's an infinite dimensional space. You have function of Z that starts from the module R lambda 1 and go to the symmetric space E11 divided by some almost compact involutive subgroup. So this, by definition, is a Cartan involutive subgroup. And the notion of Lorentzian now is kept because if I take the intersection of E11 with GL11, I get the Lorentz group in 11 dimensions. Whereas the compact case, in a way, would have been a compact finite dimensional group, so SO11.
So there is a canonical embedding of GL11 in E11. You take the one corresponding to the
So this one is not unique. And I take the one which will be defined near my identity where I want to define it. To be more rigorous, because it's Lorentzian, there is no proper E-weather decomposition. So you have Weil group elements which rotate them and which correspond to rotation of E11, so you cannot canonically define, but the theory has to be defined in the correct E-weather chamber. So all the discrete elements, for example, in E11 should not be used. And if you want E11 of Z, if I want to think of duality, include the proper duality, which are certainly E10 of Z. If you take something bigger, you would go to the Hull M star theory and things with a strange signature, which we don't want to do. At least I don't want to do. Okay, one more thing that we need for defining this theory is a property that when you have infinite dimensional representation, not all tensor products are fully reducible. And not all representation in general are fully reducible. So in particular, you start to get indecomposable representation. And in fact, I will not explain how we get that, but there is a representation adjoint at, which is a combination of the adjoint of E11 with the representation R lambda 2, which appear here in the tensor product, and which is indecomposable. What does it mean indecomposable? It means that if I act on such an element by parameterizing, for example, E11 by phi and R lambda 2 by x, when I write it as a matrix in the action, I get the standard action of E11, which I write schematically as minus f for the structure coefficient of E11. I get a representation matrices acting on x, but there is also a lower triangular piece which acts non-trivially and which I write k. So this is called a cocycle for the representation. So you also have a representation for k equals 0, but you can show that this is still a representation for a non-trivial case that you cannot eliminate. You cannot diagonalize this matrix. And for us, that's very important because this is the way we can define a representation for the notion of field strength. In the E7 theory for supergravity, there was a field strength valued in the 56th representation of E7. And here there is still a field strength. And this field strength, which I write Fi, is defined with structure coefficients, which involve both the current, if you recall, Jm alpha. Jm alpha was defined from M inverse dm M, where M parameterizes the coset, V transpose V essentially. But there is also a piece, Cim alpha tilde, with a chi m alpha tilde, which is precisely this one. So if I write indices here, it's phi alpha x alpha tilde, and which is necessary for the whole object to transform covariantly. And now this chi m alpha tilde is exactly as the chi I m I wrote for LR symmetry, meaning that they are constrained on their first indices. So this is all slightly formal. But this representation now has a very nice property, which is that it is symplectic. So there is a non-degenerate invariant E11 bilinear form on this space, which you can write as omega ij fi gj. And what we could not prove but conjecture and test on many subalgebras is that there also exists a K E11 symmetric bilinear form on this same representation. I write this representation T minus 1. as a K11 representation. That's not completely obvious for infinite dimensional representation, but it would be if t minus 1, for example, was irreducible or fully irreducible. And as far as we could check, there is no notion of undecomposability is t minus 1, but we do not have a theorem for that. So once we have this, we can just generalize the equation that was used in 4-dimensional n=8 supergravity, which now reads that Fi is equal to MIK omega Kj Fj. And because of the Minkowski signature, that's an involution, and that defines a duality equation. So what this equation includes, now we can just decompose into GL11 to see what it includes. So almost by construction, if you start with this as a first level, what you get is just the equation of 11-dimensional supergravity, which I wrote to start with. F7 is equal to star F4. But it's not only this component, it's infinitely many of them. So to actually describe this equation for simplicity, I will assume now that the field only depends on x mu, the 11-dimensional coordinate, and neglect all the others. But all those field strengths depend on infinitely many coordinates in principle. If you go to the next step and you write this equation, what you obtain is an equation for dual gravity. So on the left, you get of F mu mu1, mu2, sigma, and you can write this as 1 of square root minus g, 9 factorial of some f mu1, f mu2. I don't write the metric indices for simplicity, which are hidden here, to 9 f mu1, mu9, sigma. So this is just a flux for the metric. It can be written very explicitly as g sigma rho d mu1 g mu2 rho minus d mu2 g mu1 rho. And this is something more complicated that involves a dual graviton. But what you should see directly in this equation is that there is a problem if I want this equation to be invariant under diffeomorphism, which is that this combination of the metric is certainly not something that transforms as a tensor under diffeomorphism in gravity. But this is taken care of by the transformation of F. After that, you get also infinitely more that I may not have time to talk about.
So also in that equation, the right-hand side depends also on T. It's not just the dual gravity.
So if I was writing all the metric factor, including the raising g sigma lambda, I will write this later. Sorry, give me a minute, because I want to say something more before that. Actually, no, let me write. No, actually, you're right. I should write it directly, which will allow me to explain why I need something more. So if you write explicitly this F, it depends explicitly on the dual graviton through the current piece. So F mu1 to mu9 semicolon nu is like the divergence of the dual graviton. So 9 d mu1 antisymmetric with h mu2 all the way to mu9 colon, in that case, nu. Colon means that there is no completely antisymmetric part. There are some terms associated to A3, dA3 plus A3, dA6, which I don't want to write, but no metric. And what is important is an additional piece that comes precisely from that field, which is not in E9, but corresponds to this undecomposable representation, and which in that case is simply nu semicolon nu1, nu9. So in this way, you see that you have completely trivialized that duality equation, because here this field is not constrained at all. The constraint was telling me that the first index M has to satisfy the constraint, but if I use GL11, I simply have that M can be any of the 11-dimensional indices. So this component is anything. So the duality equation here is telling me nothing. It's just telling me that, well, the metric is related to that field. Just giving me the value of that field. And if I go on and on, well, I will get more component of chi, but nothing new. So this equation is empty if I just take it as it is. I need to supplement it with a Lagrangian. Not exactly a Lagrangian, a pseudo-Lagrangian, meaning that the Euler-Lagrange equation for the pseudo-Lagrangian, together with this duality equation, will determine entirely the dynamics. And this Lagrangian we define, I will not explain it at all, but we obtain that there is a Lagrangian which transforms as a density. We cannot really integrate over those generalized coordinates, but we can define the notion of transforming as a density such that the Euler-Lagrange equation for this pseudo-Lagrangian give rise to equation that do what we want. So how does it work with this now? This Lagrangian involves all the infinitely many fields, so it's a formal sum. So if you compute, for example, the Euler-Lagrange equation for the metric, you will get an infinite sum. But if you solve the constraint in a specific choice of parabolic, meaning, for example, this GL11, you can make sense of this Lagrangian. The way you make sense of it is by choosing a Lagrangian, not a Lagrangian in the sense of the density functional, but Lagrangian in the sense of the symplectic space. There is a natural notion of an isotropic space associated to this symplectic form, where I can decompose for the grading. This is positive grading on for the top form and negative grading for the other. I can decompose omega I1, j in this way. And what one obtains then is that L is equal to L0 plus 1/4 of omega I plus j minus. The plus and the minus means that I have chosen a polarization, where I can write the duality equation. So let me write this as epsilon I is equal to 0, and simply write here epsilon I plus epsilon j minus. So note that if I don't break the symmetry by choosing a Lagrangian, this is 0 if I sum over all indices, because omega is antisymmetric. But if I choose the Lagrangian, like it's choosing Darboux coordinate, I just have the square of each of the equation. And if I add this to the Lagrangian, what we could show is that this, in this specific case of GL11, is simply the Lagrangian up to total derivative of 11-dimensional supergravity. So now we have the dynamics, because we have Einstein equation, and we have the equation for the tree form coming from the Lagrangian, and all the duality equation now can make sense, because G is not anything, it's a solution to Einstein equation. But to make sense of this duality equation, however, it's useful to do not use the 11-dimensional supergravity Lagrangian, and to just choose the type of duality equation we add up here. So instead of adding all of them, one can choose to add only the ones that do not include the dual graviton, so that we will get a Lagrangian which involves now the dual graviton. And a priori, one can do that for any higher spin field, but let me write what it is for the dual graviton. And I need to find where I wrote it. Here it is. So the Lagrangian, when obtained in that case, is not super simple, and maybe for the lack of time, I will forget about the tree form potential, but it would be Lagrangian in the tree form. So there is a term which involve explicitly the metric. Well, I can write at least the kinetic term for the fourth form because it does not cost anything. So it's just the standard Lagrangian for the fourth form. And there is a kinetic term for this field strength, which I wrote up there. And this kinetic term takes this form, mu h, mu semicolon sigma, f mu 1 to mu 8, sigma semicolon nu. So you just inverse the two last indices. And to this, you have a topological term. You just have the standard 1,6 A wedge F, which I don't take the time to write explicitly. And then you have one additional 2 times 8 factorial, epsilon mu 1 to mu 11, g nu sigma, d mu 1, g mu 2. So this is kind of gravitational flux. And F sigma mu 3 all the way to mu 10 semicolon mu 11. And now the idea is that this is an actual Lagrangian for the theory. So how you can interpret it? Well, you can interpret it very similarly to something that has been done before by Boulanger and Home, but in the Filbine formulation, which is very similar to this. That is, you interpret this as what they call a Stuckelberg gauge field, which a priori trivializes completely the dynamics. So if I start by integrating out this field, which is auxiliary in this Lagrangian, it does not come through derivative, it comes quadratically through this term and here. You can just integrate it out, and what you will get back is just 11-dimensional supergravity Lagrangian. But you can choose instead to first integrate the metric field. So for this, you have to note that also there is this term. This term does not propagate. If you linearize the metric as g mu nu is equal to eta mu nu plus a variation that you consider as small, then this term drops out at the quadratic level. Because of the antisymmetry in the derivative here, you don't get anything. So this term starts contributing at cubic order and more. And now if you take the equation of motion with respect to the metric, you have some expansion which has very first order, at linear order, is an integrability condition for f. So essentially what you get is d mu 1 of f with the special indices, the first one, mu 2 all the way to mu 9 semicolon mu 10 antisymmetric. So it's not exactly 0, right? It's equal to term which involve g minus 1 dg to the square plus g minus 1 dg times f, this f91, and terms which involve f4 square. But if you do a linearized analysis, this is just 0. And now if you solve for this equation in the linearized approximation, you obtain by generalized Poincaré lemma that chi nu is a total derivative. So in that form, f mu 1 all the way to mu 9 semicolon nu just gives d mu 1 h mu 2 all the way to mu 9 nu plus d nu x mu 1 mu 9. And in principle, you can go on and on. That starts very quickly to be very non-local and very difficult, probably. But in principle, you have this notion now of the dual graviton. And you can check that this is just the propagating dual graviton, meaning that if you take one more derivative and antisymmetrize with the new index, the x disappears, and you will get just the linearized relation with the linearized Riemann tensor, meaning that d nu 1 f mu 1 mu 9 mu 2 antisymmetric is like epsilon of mu1, mu9, sigma rho of R, mu1, mu2, sigma rho at the linearized level. So you get exactly the same degrees of freedom. Now the idea is that you can repeat this operation for all the other. I did not take the time to explain, but what you get at the next level are still yet propagating field, which will be associated to a 8-9-3 form, which is again dual to the derivative of the 3 form. And with arbitrary many 9, you just get arbitrary many gradients, and you can write Lagrangian like that. We only wrote it explicitly for the 9-3, but for the 9-3, you have exactly the similar type of action at the nonlinear level, where you can either get back 11-dimensional supergravity by integrating the corresponding chi field, or obtain the linearized duality for this field. And the idea is that all the ones that come at linear order, the ones that I described in the affine subalgebra, are the propagating fields, which are dual to the original field, which is something that was already claimed a long time ago by Peter West, clarified to some extent for those gradient fields also by Boulanger, Sandel, West, and which this proposal makes clearer. There are also infinitely many more field strengths and fields, but all the other ones are pure gauge. And you can find that the duality always relates them to field which involves the other derivative. So if you take this solution, they all trivialize to 0. And this is the only thing that remains in the model. So I wanted to make a small connection to E10, but I don't think I have a time for that. So I will simply conclude with this. So what we have proposed is that there is a nonlinear theory based on E11 function of the R lambda 1 model. Quite importantly, there is this field strength representation which gives the duality equation of the form M omega F, and that involves the indecomposable representation adjoint, which involves both E11 semi-product with this R of lambda 2. What one I did not explain, but all of this, the algebraic relation, are based on a superalgebra T of E11, that was first proposed by Jacob Paltrust. And if one do GLD times E11 minus D decomposition, one gets the exceptional field theory proposed by Ohm and Zemsleman. So that we checked for E8, and by construction, then it's true for any intermediate case. What would be more interesting, and we only started to discuss in the paper, is what happens if we take instead just GL1 times E10, because in that case, it's supposedly related to the cosmological billiard that Marc will explain to you in the following of his lecture. And essentially, the same as the gradient expansion should be now to neglect the internal derivative of all field corresponding to the E10 direction. And what one obtains, at least in a very naive sense, is that the Lagrangian can reduce to the nonlinear sigma model for E10. But with one additional constraint, which is related to those constraint fields, which tell us that E minus 1 J T alpha is equal to T alpha Mn pi Mn. So this may sound that a constraint that does not give anything, but because of the constraint index, that gives an algebraic constraint on the corresponding current. And now I will thank you for your attention. Sorry for the many indices and